again listen. Okay, with Newton's law of cooling, just like growth and decay, we are representing a certain rate, in this case, the rate of change of the temperature of a body, or the rate of change of the temperature of a cooling body specifically. And the manner we represent it is exactly the same as that in Newton's law of cooling. So since according to Newton's, rather it's the same with growth and decay. And since Newton's law of cooling states that the rate of change of the temperature of the body is proportional to the difference between the temperature of the body and that of the surrounding medium, it is represented by d capital T dt with the direct proportionality symbol here, and then that would be the difference between the temperature of the body here, which is capital letter T, at any particular time in small letter t, minus the temperature of the medium or of the surroundings where the body is placed into. Now, we will get rid of the proportionality symbol, and as I have already illustrated that when I derived Newton's rather growth and decay problem, we replace the proportionality symbol by an equal sign, and we introduce a certain constant. So this is now our differential equation for Newton's law of cooling. The rate of change of the temperature of the body that is cooling down is equal to the product of the cooling rate constant K, we call this the cooling rate constant, and the difference of the material's temperature or of the body's temperature with the surrounding medium. We place a negative sign here because this actually derivative, the d capital T dt derivative, is a negative. So we transferred the negative sign in here on the left side to the other side. Anything that is represented by a decrease in the value over time is, in terms of a derivative, is negative because the final value is less than the initial value. So if we take the difference, that would be a negative. So that we won't be having problem with dealing with the signs, we already accounted for that negative in here. That way, all the time, as I say all the time, the values that you should be getting is positive. So whenever, whatever you calculate concerning application of first order differential equations, with reference to the differential equation itself, all the values has to be positive. Even the rate constant has to be positive. We shouldn't be getting any negative value because we already accounted for that in here by the placement of the negative sign. So let's define the variables that you are seeing in the formula. So the capital T is the temperature of the body at any time T. At any time means it could be the initial start of the cooling of the body, or it could be any time after the cooling process already started. Okay, that's your capital T. The T sub M is the temperature of the surrounding medium or of the environment where your body is placed. Now, if we will process this dE, and I leave that to you because the derivation of this formula is exactly the same as that in growth and decay, your formula coming from this one, after we have separated variables here and considering T sub M as a constant, would be this. So whenever you solve problems concerning Newton's law of cooling, you need not go back to the original dE. You only have to go back to this formula. So the formula tells you that the difference between the temperature of the body at any particular time with the surrounding medium is equal to the product of a constant C and the exponential function, which accounts for the time of cooling and the cooling rate constant. So this capital C and this cooling rate constant K will all be determined based on the conditions that are stated in the problem. So again, the C and the K has to be determined based on the condition that is stated in the problem. Then after you have determined the two constants, that's the time that you are going to determine the actual required information by the problem. It could be the temperature after cooling commenced, or it could be the time needed for a temperature value to be reached. So that's in case of the use and the understanding of this formula for Newton's law of cooling. Now, there are very important assumptions that you need to understand when we apply Newton's law of cooling. And actually, the number one assumption is this, that the temperature of the cooling medium, or the temperature of the environment where your body or your material is placed into, is a constant, meaning it will not be affected by the transfer of energy from your body or from the material to the surroundings. So that's it. The surrounding medium temperature should be a constant, and it's written here in the third bullet. And then the loss of heat here is purely by means of radiation. So we don't have convective heat transfer, and we don't also have conductive heat transfer. The first bullet talks about the allowable difference between the temperature of the body and that of the surroundings, and it says that it should be small. Okay, meaning we're not expecting a difference in T and T sub m that is very large. So it should be a small difference only. So these are the assumptions and the limitation of Newton's law of cooling. Okay, now we will go to sample problems. I have prepared three here. I think three would be enough to illustrate the application of the principle on the derived formula that I have already shown to you. So it's in my handwriting, and I'm not anymore using the board because sometimes writing on the board, if can be eliminated, is really taking much time. So what I have prepared here is already the solution, the ready-made solution of the three problems. So let's go first to problem number one. So a body at temperature 40 degrees Celsius is kept in a surroundings of constant temperature 20 degrees Celsius. So this is the surrounding temperature, and this is initially the temperature of the body. It is observed that at its temperature falls to 35 degrees Celsius in 10 minutes. So after 10 minutes, we observe that from 40, the temperature of the body decreased to, or was reduced to, 35 degrees Celsius. Now, with this condition that after 10 minutes, there has been a decrease in the temperature of the body to 35 degrees Celsius, we find how much more time will it take for the body to attain a temperature of 30. So you have to be very careful as to the actual required information in the problem. So it says here, find how much more time will it take for the body to attain a temperature of 30. How much more time, then it must be referring to after 10 minutes and your body is still to be cooled down to 30 degrees Celsius, how much more time will be added in the cooling process. Okay, but we cannot solve this how much more time directly. We have to determine the actual time from the starting temperature to this 30 degrees Celsius, and then later on subtract the 10 minutes that it would take for the body to reach the temperature of 30 degrees Celsius. So I will show to you the solution. So the T sub O that I have written here is the initial temperature of the body. So that's your a body temperature of 40 degrees Celsius, telling you that that's the initial temperature. So in here, we will represent initial temperature as T sub O. If you want to represent it as T sub 1 or T sub I, as long as you define it later on when you write your solution, I don't have any problem with that. It's just that we're used to representing here original temperature or initial temperature or temperature at time 0 as T sub O, because this one, the 40 degrees Celsius being the initial temperature of the cooling body, is the cooling temperature of the body at time 0 at the start of the cooling process. So that's the main reason why I suggest that it should be T sub O. The surrounding medium temperature was already stipulated in the problem to be 20. And It was noted that after 10 minutes in these surroundings, the temperature decreased to 35. So you are required for that how much more time for T to reach 30 degrees Celsius. So you have to make use of the conditions initially stated. So the original temperature, that's the time zero temperature, is substituted for the T in here. And the medium temperature or the surrounding temperature is 20, equal to, equated to CE raised to negative K times 0, because the T sub O is equivalent to times 0 for the process of cooling. Using the first condition, the first given information allows you to determine the C, the constant that is present here in the formula. So once you have determined that already, you can now change the C here to the actual value that you got. Then you use the second condition. So the second condition says that after 10 minutes, it was observed that 35 degrees C is already the registered temperature of the body. So your T now will be 35. You will need to subtract the same medium temperature, which is 20, because there was no mention in the problem that your object or your body was transferred to a different environment. Then your T sub M would still be a 20. Then it's equated to 20 e raised to negative k, and you substitute the time here, which is 10 minutes. Now, in the process, you'll get the cooling rate constant value of 0.0288 per minute. So it is very important that when you write solutions, especially if it's an open-ended problem, you have to indicate the correct units. So since your time unit is in minutes, then it should be also per unit time here in minutes. Now, the generic formula now is more specific to our problem. So the two constants were already in place based on the conditions that we used to determine them. Now, it says there, how much more time you need for the temperature to even decrease to 30. So your T now will be 30. Your medium temperature is still 20. And you have here 20 e raised to negative 0.288 or 0.0288 T. This will allow you to solve for the time. This time class is starting from the initial value or the initial temperature of the body, which is 40. It started with 40, then it cooled down to 35, then it cooled further to 30. So this 24 is actually the time elapsed from the starting temperature for cooling to commence. Then the added time must be how much time would you need to extend cooling from the 10 minutes wherein the body has already decreased to 35 degrees Celsius in temperature. So that would be simple. You subtract the 10 minutes from the 24. So this is the added time. Now, how much more time will cooling the body proceed so that it will be decreased to 30 degrees Celsius, referring to its temperature. So the how much more time in reference to in here is based on the after the 10 minutes wherein the body has already reached 35 degrees Celsius. So this should be your answer for this problem, not the 24.07. Because if you will understand the problem, the cooling process is from 40, then it was reduced to 35, then it was reduced further to 30. So the phrase how much more time should be understood that it should be measured from the 10 minutes here, wherein the temperature of the body has already decreased from 35 degrees Celsius. Okay, so that's how you should understand this particular problem, or this is how you should determine the unknown information. So your answer should be 14.07 minutes. That's for the first sample problem. You have any questions? Do you have any questions here on the solution?
None, miss.
Okay, so if there is no question, then I'll go to the second problem. Should we be disconnected, we will use the same link just like what we do before. Okay, the oil is heated to 70 degrees Celsius. Now, after the heating process of the oil to 70 degrees Celsius, it was cooled down. So it cools to 50 degrees Celsius after 6 minutes, meaning the heating process already stopped here on this temperature because cooling process already commenced. It's very ironic for the temperature to decrease to 50 degrees Celsius if heating did not stop here. So it will only cool down if heating already stopped. So after 6 minutes, the temperature of oil decreased to 50. Now calculate the time taken by the oil to cool from 50 to 40. So take note, it says here you are to determine the cooling of the oil from 70 to 50. And then now you are to calculate the time by the oil to cool from 50 to 40 degrees Celsius. Okay, we'll go now to the sample problem. Okay, so sample problem number 2. Now, this is our initial temperature, and this is the temperature when we started after we started heating. So this happened after 6 minutes. The cooling started. So stop na di ang heating. Then we did cooling for this oil, and this it's happened here for 6 minutes. Then temperature of the medium, did not mention it. So the surrounding temperature T sub S here, or the medium temperature, is 25. So that's our T sub M, which is 25. Now you are asked to determine the time for the temperature to cool down from 50 to 40 degrees Celsius. Now, is this problem same as this? Number 1. Will this problem be, in principle, be similar to number 1? So calculate the time taken by the oil to cool from 50 to 40. Anyone in the room?
Yes.
Yes, the answer is correct. So it's just like this one, only rephrased in a different manner. The manner of asking the question is different, but it's similar in principle to number 1. The only difference here is the object that is cooling down. In here, it's generic. It's the body. Well, this one is the oil. Meaning you are to determine the temperature it would take for, rather the time it would take for the object to decrease its temperature from 50 to 40. So it's the same oil that we're talking about. So now we go to our solution. Okay? So same in principle. For condition 1, you're given that the initial temperature is 70. So 70. 25 is the medium surrounding temperature. C e raised to negative kT. So the purpose, the T here again would be a 0 if our temperature is 70. So the purpose is in determining the C, which is 45. Okay? Now, we determine the K. So it says there that it would take 6 minutes for the body to cool to 50. So 50 here for the temperature, T sub M is 25, and you have here 45 e raised to negative k times 6. 6 minutes here. 45, which is the constant we determined in the first condition, was already substituted. That allows us to determine the cooling rate constant. Now, the cooling rate constant of the body class is already placed in here, the negative 0.098 T. And if you notice, I placed the C here again. So for a different take on this, I'd like you to get a piece of paper there because I think I solved this differently. How will you determine the time for your object to cool down from 50? So it says from 50 to 40. So I will be waiting for 5 minutes for you to do that. Let's see if my answer here will be correct because I did an experiment here, and let's see if this will work. So you will determine now the time for the temperature of the object to decrease to 40 from the temperature of 50. Can you do that? I'll give you 3 to 5 minutes to do that. You have it? I already have it. Anybody? What's the temperature that you will be getting if the object is cooling from the original temperature of 70 to 40? What's the time that you will be getting?
11 minutes ang almost. So,
Very good. So that's 11.2103 minutes, right? Now, if you're going to subtract, so it took the oil in the first condition here 6 minutes. So 10 minutes na lang ko, no? We will just reconnect. It took the oil 6 minutes to reach the 50 from the 70. So from the 50, from this temperature here to 40, how long did you cool down the object? So all you have to do is what? All you have to do is, anybody, you say it's the same principle as number one. So all you have to do is time to decrease from 50 to 40 degrees is what? Hmm? Anyone?
minus sa 11 minutes.
Correct. So kung i-minus, talangin siya sa 11, your answer should be 5.2103, right? Did you get that answer?
Yes, Miss.
Okay, so let's see what Miss Ali did here. Let's see if the answer of Miss Ali will be comparable to yours. So it's 5.213. Now, this is a different procedure than what you did in number one. Though, as I said, they should be applying the same principle. What I did here is this. Isn't it that we will be starting from a new temperature to start counting the time it would take for cooling to reach 30? That new temperature is the 50 because the problem is saying how long will it cool down to 40 starting from 50. So what I did here, I computed again for the C. The C wherein my initial temperature is not anymore 70, but I use already the 50. Now, of course, my time would still be 0 because this is to be interpreted as this is my new starting temperature for cooling. So the C that I'll be getting is not the C here, which is 45, but this time it would only be 25. Now, you may ask, why did you not change the K? Your K here above, which is 0.098, is the same K that you used here. The answer is very, very simple, class, and you have to understand this principle. The rate constant of the object is not dependent on from what particular time it undergoes cooling. It is not even dependent on the surrounding medium where it is located. So meaning if this oil is cooling down in the Philippines or if this oil is cooling down in London, the K is still fixed because it's a property of the material. So I don't change the K because it's still the same wherever my oil is located or wherever is my object is located. So I still use the same value for the K. So now I would want to know the time for my object to cool down from 50. It says here from 50 to 40. So now I place here a new T, which is the 40. I still have a TM of 25. I now use the C, which is 25. And there you go. The time is 5.21 minutes. Isn't this the same as the value that if you do subtraction, this is the same value, right? So you now have two options to tackle any problem concerning a cooling from a set of given temperature to another set of temperature. So you need not like subtract like the way we did in number one, but you can use this particular approach. But again, this is just an option. That is why I really indicated conditions here. This is condition one, wherein cooling is from 70 to 50. And I place here condition 2 wherein cooling time is to be measured from 50 to 40. I'm not saying that you use this particular procedure. This is just an option. If it's much clearer to you and more understandable that you use the first principle or the first procedure in sample problem number one, it's fine, class. I don't mind. I'm just giving you here an option or a different procedure of determining the unknown. Do you get it? So it's just another procedure to determine now. So this time we did not do subtraction anymore. We actually determined the time for the object or for the oil to cool down from 50 to 40 without doing subtraction. Okay, so that's just an option. Now number three, I'll give you an overview of what is number three. I'll read the problem first. Suppose that a body of a dead person with temperature 85 degrees Fahrenheit was discovered at midnight. It was found somewhere, and that the ambient temperature in the location where it was found is 70 degrees Fahrenheit. Now, the body was removed quickly from that environment, and we are to assume that it's instant. The transfer of the body from the surrounding where it's found the dead body was found is almost instant. Of course, class, this is a very crude assumption. Of course, everybody will not agree. What if the body was found in, for example, in San Carlos, and it was placed in a morgue in, let's say, what's the nearest city to San Carlos? I do not know. Let's say it was placed in a morgue, let's say, a 10-minute drive from where the body was found. So it's not instant. But in here, the problem says that the removal of the body from the scene where it was found is almost instant or assumed to be instant. And this is when you are doing what you guess it, crime investigation. This is a very crude assumption. But just for the sake of illustrating the application of Newton's law of cooling in estimating the time of death of a body of a person, then we will assume, or the problem uh, said that you will assume that it's almost instant. Now, the temperature in the morgue is of course different than the temperature of the surrounding where the body was found. It's maintained at a temperature of 40 degrees Fahrenheit, very cold, because 32 degrees Fahrenheit is already zero, near freezing. So this is just a little above 0 degrees Celsius. After 1 hour, that the body stayed in the morgue, its temperature increased or decreased to 60. From 70, where it when it was found, now it turned into 60. You are to estimate the time of death or the time of death of this particular person whose body was found at 12 midnight and whose temperature registered 85 degrees Fahrenheit. Now, when you solve problems like this, class, and this is the challenging part of Newton's law of cooling, if it's just problem 1 and 2 types, it's very easy. I'm sure a lot of you would be able to understand what to do. In number 3, you have to plot the time the temperature, and the surrounding medium where the body was transferred into. That way you will have a clearer understanding of what particular values you will use, because the problems in the general reference book that we are using then in DE, which is elementary differential equations by Love and Rainville, are not as simple as this always. These problems are challenging because there is a transfer usually of the object from one surrounding to another. So how will you process this kind of problem? So this is how you do it. Okay, number three. Now, what I did is I plot the time, the temperature, and the surrounding medium that is being that is to be rather identified from the problem. So it says in the problem that at 12 midnight, a body at 85 degrees Fahrenheit was found, and the surrounding temperature where it was found is 70 degrees Fahrenheit. Now, I place a parenthesis here because this is a very crude assumption. Kay almost instantly, meaning when it was found, it was transferred right away to the morgue. And if it's to be transferred to the morgue, of course, it would entail time. But in here, there was no mention of how long it took the body to be transferred to the morgue, but almost instantly. So it's still 12 midnight then. You may wonder it's still 12 midnight because of the assumption. The assumption here. Assumed instantly. The body was removed quickly, assumed instantly to the morgue. It was placed in the morgue where the ambient temperature is 40. So now I have plotted here a temperature that is similar at 12 midnight, but this time the surrounding temperature is already 40. Then the problem says that after an hour, the body in the morgue registered 60. So then after an hour, 12 midnight, and that would be 1 a.m.